Okay, hello everybody. It's good to be here and talk about numerical relativity. I am now at the Albert Einstein Institute in Potsdam. I go back to Cornell University where I did my PhD with Saul Tucholsky in numerical relativity. Saul is also one of the authors of numerical recipes. Did postdoc work at Caltech and then was a faculty member at Toronto at CETA for quite a few years. And as I just pointed out, moved to AEI recently last year. And our topic for today and the next 2 days is numerical relativity, solving Einstein's equations with big computers directly. This is necessary because all the other nice things you know about GR often don't work. If you have symmetries, life is good, because with enough symmetries you can write down analytic solutions. And this works both for the usual black hole solutions, so Schwarzschild curl, where one of the symmetries is time and you have one or two spatial symmetries. But it works also in the opposite way, where you have more spatial symmetries. If you have enough spatial symmetries, then you can tolerate time dependence, and that way you get the cosmological solutions, like Friedman-Robinson-Walker. If you have not enough symmetries, but still some small parameter, then you can go towards perturbation theory and to perturbative solutions. And there's quite a few different regimes you can go into there. One is that you have a small metric perturbation, for instance. That leads to linearized gravity. Gravitational waves, but also quasi-normal modes, black hole ring-down theory, is in some sense living in this limit here. Quasi-normal modes. If you have large mass ratios, say you have two bodies, and the second one is much smaller than the first one, then you can do a perturbation theory in the mass ratio of the small body. And so this is then now going roughly into the gravitational self-force. And I think Eric Poisson talked about this last week, didn't he?
Yeah.
And if you have small velocities, then you can do post-Newtonian theory, the topic of Cliff Will's lectures later this week. And there's a lot you can do in these regimes with small parameters, because these regimes tend to be quite important. And also, people working in these areas are very audacious and pushing perturbation theory to often very, very high order, especially in post-Newtonian theory. Gravitational self-force is on the brink of getting second-order results. Linearized gravity usually well is linearized gravity. But in the absence of all these things, there's still a lot more to be done. And so otherwise, if life is nonlinear, if it's dynamic, if you have full 3D without any symmetries, then typically the only way to solve these problems is putting them on big computers and directly trying to solve the full Einstein equations numerically. The This is, like all the other topics in relativity, also quite an old subject area already. Just to give you a few pointers over the years, the first actually numerical simulations for involving black holes were in, does anybody want to guess when? Not bad. 1964. Hahn and Lindquist. Did the first evolution of wormholes. They used a grid with a total of 51 by 51 grid points and did something like 150 time steps. So really early started, but the first actual computation involving black holes and trying to solve general relativity. In the 70s, around 75, 77, the next two guys came along trying to solve Einstein's equations, still head-on, still not working, or kind of working in axis symmetry, Larry Smar and Ebley. In the 90s, 94 to 98, by this time LIGO came around, and so it became clear that being able to know what happens when two black holes collide and how the waveforms are looking like will be essential for LIGO data analysis. If you don't know what you're looking for, it's really hard to find those types of waveforms. And so in the 90s, when LIGO was being built, this became ever more urgent. And the NSF, the US National Science Foundation, set up a binary black hole grand challenge, where the whole community in the US, the whole approximately 10 or 15 people or so working in this area back then, were supposed to work together and get the problem done and actually evolve and solve the collision of two black holes on computers. The outcome of this enterprise was basically that the realization that solving Einstein's equations is really, really hard. And that there were a lot of technical problems and conceptual problems that still needed to be solved back then before one could actually successfully do this. And so what the binary black hole grand challenge did, I have a computer here. I didn't plan to do this, but since I have a computer here, let me try and find the plot. And of course I should never do this, because whenever you try to do something on the fly, chances are it will fail. Perhaps I have it in this slide. Let's see. Yes. Hey! That's not what I wanted to show. What the outcome of the binary black hole challenge was, this is a space-time diagram. Space is going wide. Time is going forward, up here, this direction. And so what they managed to do is they started with a black hole at the origin, going from plus minus 1 in these units. And they managed to be able to evolve this black hole as it traveled through the grid by about 1 diameter. And after having just a single black hole traveling for 1 diameter, the code became unstable and blew up, and they weren't able to continue this simulation. So this is one of the two prime results of this 4 years of the black hole grand challenge. It is a difficult problem. The other big outcome of the grand challenge has to do with how gravitational waves are propagated to infinity, the Cauchy characteristic extraction of black holes. So after this, and even beforehand, in the 90s and the 2000s, a lot more theoretical work and also numerical improvements work on how one deals with constraints, work on how one actually writes down equations such that a computer has a chance of solving them. This leads into hyperbolicity, a topic we will talk about a lot later today. A lot more numerical algorithms, adaptive mesh refinement came out of this phase. The pseudospectral methods that I'm also going to talk about later today, they were also first developed in the late 90s, early 2000s. So improvements at many, many different puzzle pieces of numerical simulations. And then everything got together quite rapidly in 2005, 2006. 2005, first Pretorius presented a full simulation of two black holes orbiting about each other and colliding. With one particular way of rewriting Einstein's equations that goes under the name of generalized harmonic. We'll talk about what this work means tomorrow. And a little bit later, so this was early, and in late 2005, two other groups situated at Goddard Space Flight Center and simulated at Brownsville, they both independently got moving punctures. Evolutions working. So within about a year, the field went from nothing really works to, hey, we now can solve orbiting and colliding black holes with two entirely different formalisms. A year later, my collaboration came along. The collaboration is now called SXS, Simulation of Extreme Spacetimes, writing the spec code, the spectral Einstein code. And that code hasn't been the first, but also, as I'm going to explain over the next few days, is the most efficient, most accurate code to solve binary black holes these days. So suddenly, within about a year or two, there was this big phase transition. Nothing worked, a lot worked. And since then, a lot of results are rolling in on various aspects of numerical relativity. And of course, the really big thing that happened was 2015. The gravitational wave observations. The first gravitational waves were binary black holes. The very first one was actually loud enough that you could have just detected it without having waveforms to search with. But still, knowing the shapes of the waveforms was very helpful because it increased the significance of the detection. And knowing the waveforms was essential for some of the later weaker signals. Otherwise, they wouldn't have been found. Figuring out what we have seen in LIGO works by comparing the gravitational waveforms that were measured with what you expect the waveforms look like for black holes of different masses and different spins. And so, for LIGO to actually measure black hole quantities, parameters, masses, and spins, one needs to know how the shapes of the waveforms work. Numerical relativity is essential there because the black holes that LIGO are seeing were unexpectedly massive, 30 solar masses each, so that the merger part of the waveform is the most important one in order and carries the most signal-to-noise ratio for the observations. And if you want to test general relativity, well, you test general relativity. In order to test general relativity with gravitational waves, you must know what the prediction of general relativity is. Otherwise, you have no clue how the actual observation relates to the prediction of GR. And so in all these parts, detection, parameter estimation, which is often abbreviated PE, as well as testing GR, numerical simulation played a very central role. I very much appreciate working interactively. So if there's questions, please speak up at any time.
Yeah. So I suppose throughout all of those years they used different formulations of general relativity. I mean, I would suppose the first word was still canonical GR, but then for the Harald collision, you already had the 3+1 foliation.
Okay, yeah, I'll be talking more about this in the next few days. There's also more in this category which I didn't put down. So 62, Arno, Videsa, and Misa developed the ADM equations. And this is great, and I will also present them to you guys tomorrow. And those ADM equations were basically used in all of these things over here. And one of the difficulties that came around is, and that only was realized in part down here, one of the things that was realized down here is that using the ADM equations is a really bad idea. They are what is called ill-posed. And so you can't really, they look like they are evolution equations, but if you put them on computers, it turns out they have bad kinds of solutions that will trip up the computer. And that was one of the reasons why up here very little worked. And one of the important things is that these ADM equations that were used in early work were then replaced by different ways of writing Einstein's equations that turn out to be much better for putting them on computers.
Is there a general agreement nowadays about which formulation is the best one to use?
No. There's two that are in widespread use, and they both seem to be working quite well. And it's actually really great to have two independent ways of solving Einstein's equations, because it gives redundancy and it gives confidence that what we are doing actually is correct. If you build instruments that cost $500 million and they rely on computer calculations, you don't want to mess up. The same is true, by the way, for instance, for both Newtonian calculations and the gravitational self-force calculations. All these calculations are so ridiculously complicated that you need independent teams addressing the same problem several times with different methods and eventually actually agreeing and finding the same answer. Usually what happens is that this is not the case. If a new post-Newtonian term comes about, early on quite often the different groups using different techniques disagree slightly on the result, that a certain coefficient has a different value, and then everybody goes back and rechecks their calculations again, and ultimately everything is brought into agreement.
Just another quick question. Let's say you have like a binary system, as complicated as. Do you really do a 3D grid, or do you need like a 4D grid? Can you always get rid of the decouple the envelopes, so you don't need to integrate in as a multiple envelope?
One usually has a 3D grid in space.
Okay, close.
And then goes forward in time step by step. Good question. We'll talk most of today about exactly that type of setup. So there's three components or three aspects to numerical relativity. The first one I've already very briefly alluded here on is how do you take differential geometry and Einstein's equations and turn them into equations that you can actually put on computers. How do you reformulate Einstein's equations in a way to get a set of equations that is well suited? The second big step is to then teach the computers to actually solve whatever equations you now have. So you need to develop and implement numerical codes. And the third step is to do physics, to use the tools you now have developed to address the specific problems you're interested in. And if you want to solve cosmology, the whole universe, you would use your numerical codes differently than if you want to solve a black hole. If you want to do a neutron star, it's again quite differently from, say, a small body falling into a big black hole. Ideally, it would make a lot of sense to go through these topics in this order, because then each one depends on the one above. However, the way the schedule worked with our workshop session this afternoon, I will reorder, and we are going to talk today about how one actually programs computers to solve partial differential equations. And tomorrow, we'll talk about what precise equations one would actually use for general relativity. And then, roughly speaking, on Wednesday, we'll be talking about the physics and what choices to put in and what came out of all these computer tools. My handwriting, are you able to read this or is it too bad?
You can guess.
I should warn you that I'm quite childish, I find, in the sense that I try to write nice, and as kids get ever worse with their homework, my writing gets increasingly bad until somebody points out that I should be writing better again. So please do so.
Is writing larger? A little larger?
Okay. Before I actually start, let me point out a few books that might be useful. The most important book these days for numerical relativity is the really nice one by Baumgarten and Shapiro, Solving Numerical Relativity. And then, because today is Numerical Methods Day, I also have a few books on numerical methods here. Baumgarten and Shapiro, Numerical Relativity, that is from Cambridge University Press. For spectral methods, which is one of the three methods we're going to discuss later today, the little book by Thornberg is actually quite good. Thornberg. I always like books where it already says practical in the title. Methods. And this is also CUB. Discontinuous Galerkin has also one essential book to it by Hesthaven and Warburton. I should at least write the authors such that you have a chance of reading them. Nodal discontinuous Galerkin methods. And this is not CUP for a change. And I'm still a big fan of numerical recipes, even after many, many years. And the third edition has quite a lot of new and improved material compared to the earlier ones. Also, quite recently, I became aware of this nice little book, Student Guides to Numerical Methods. I haven't really looked into it a lot yet. I just got it 2 or 3 days ago. It looks quite nice as well. So all of these I have here, and you can pass them around if you guys want to take a look. If not, they're also around here on the desk in the break. Okay, it turns out that numerical relativity at the end of the day turns into partial differential equations. And so we'll need to talk about how one actually solves partial differential equations. To remind you, there's 3 different flavors of partial differential equations around. One of them are elliptic equations. The prototypical example is the Laplace equation, with or without a source term, doesn't really matter. And this is solved on some domain omega, which you can think of, for instance, a square. So elliptic equations are space only. There's no time in here. And if you want to solve Laplace equation, you need one boundary condition on every part of your boundary. So boundary is, well, no surprise, they're the boundaries of Fifth here. And you can put down different types of boundary conditions. You can have Dirichlet, they're called Dirichlet conditions, that you're specifying the value of u on the boundary, or on some part of the boundary you omega 1. Or you can have von Neumann conditions, where you're specifying the normal derivative of your function, the first derivative, the gradient in the normal direction. Or you can have more complicated ones, but fundamentally you need one condition, whatever type you want, everywhere on the boundary. You could also have, sometimes you also have asymptotic fall-off conditions. For instance, you might want that u goes to 0 as x goes to infinity. That's also perfectly fine. And that also selects then certain solutions of your equation. Once you have boundary conditions, one solves the elliptic equations all at once. There's no sub-steps involved, no time step, no anything. And if you wanted to go more complicated than just, say, this type of usual Laplace equations, you can consider more complicated equations, and then they typically end up as some combination of second derivatives. Of the variable u you're solving for. And this can then have various other terms without second derivatives. And the important thing about elliptic equations is for this matrix A here to be positive definite. And for a Laplace equation, well, this matrix A is just the identity matrix, and so that's clearly positive definite, so you're fine. Elliptic equations play a big role in setting initial data for Einstein's equations. We'll get to that tomorrow. The second type of equation are hyperbolic equations. Here again, the prototypical example is quite simple. This time around, we're looking for a function of x and t, space and time. And the prototypical hyperbolic equation, I need to get the sign right, there's a minus sign here. Is the wave equation. It can have a source term, or it need not have a source term, doesn't really matter. Where you have the second time derivative of your function, and second spatial derivatives. So it's a function of space and time this time around you're looking for.
I think the wave equation is parabolic, right? Hyperbolic.
It is hyperbolic.
Okay.
Hold your question, I will mention parabolic in 5 minutes. So this time around, the way this works is we need time, so let's have time go up. And somewhere, say at time equals 0, we begin. We also still have space, some spatial domain omega. And now we want to fill in some volume of space-time. Say from time to 0 to some time t final. And so, as you already see, by me drawing this and by putting x's and t's here, compared to elliptic equations, we have space and time. And the other really important thing here is that we want to have causality in this thing, and we want to have that the future follows from the time, so from the past. So the picture is that we start at some initial time with some initial data here, and then this is going to be evolved forward in time according to whatever the time derivatives tell us how the data should be changing as you go forward in time. So the type of boundary conditions used here is quite different from what's done for elliptic equations. We need initial conditions. And we need two of them. Typically what one specifies is u of x comma 0 equals something. And one specifies the first time derivative, u dot of x comma 0 is something else. So we have one, essentially you set u and u dot, and then the evolution equation tells you the second time derivative. And that way you can now go forward in time. We also need boundary conditions on these boundaries here. If you have them, because there could more information enter your computational domain from through these time-like boundaries, left and right. Boundary conditions are only necessary on time-like boundaries. If this here were a space-like going out towards the right instead of going up, then this would be part of the initial conditions. So typically what we need there is something like u of x comma t equals, well, something, some given function, for x on the boundary and for t in our all in time along. Precisely how many one needs here will depend a lot on the precise equation one is interested in. For the scalar wave equation that I've written down in the first line, you would need one. But we'll talk later about when this is getting more and when this is getting fewer. And finally, there is no condition at the end. So in some sense, if I wanted to color here all boundaries where we need boundary conditions, we need to put conditions down here, and we need to put conditions on all the sides. But we do nothing on the top. Whereas for the elliptic equations, We need conditions all around. The other nice thing and really important thing for hyperbolic equations is that there is a maximal speed of information propagation. And for this little example equation I've put down up here, this maximum speed is the constant c sitting in front of the Laplacian. And so you have maximum speed. With the maximum speed, there comes domain of dependencies. For instance, if you have some initial data here, and you have some certain range for the initial data, then you get this future domain of dependence based on whatever wave speeds you have, where the solution is entirely determined by the initial data. Okay, questions so far? Oh, before I erase the elliptic equations, you can also, one way to generalize this type of writing a second order hyperbolic equation is again writing it with a full matrix formula. But this time we need space-time indices, A, mu, nu, and then we have d squared u dx mu dx nu. And this time around, the important thing is that the eigenvalues of A must have exactly one minus sign and everything else plus. And that minus sign then turns into the time axis.
If this is satisfied, maybe the problem is well posed, or there is an extra condition?
There's a lot of more conditions. Since you already mentioned parabolic equations, let me briefly put on parabolic equations as well, which would be the third type of equations that exist. And that basically has a first time derivative coupled to second spatial derivatives. Equal again, can be again source terms on the right hand side. Parabolic equations, the prototypical parabolic equation is heat conduction. If you want to consider how heat distributes itself around, the change in temperature at a certain point in space has to do with the Laplacian of the spatial temperature gradient. Parabolic equations have infinite propagation speeds. So they are violating causality, or the speed of light. If you want to be precise, and they are mostly irrelevant for numerical relativity. They only show up in apparent horizon finding, when one already has a numerical solution and wants to localize where black hole horizons are. Okay, the one we will spend most of today about are the hyperbolic equations. I've introduced hyperbolic equations so far as second order equations, but it's actually a lot more convenient to rewrite them in first order form. That makes it easier to write down a coherent formalism of how to address well-posedness and how to put them on computers. So let's talk about what's called a first order reduction. Of the scalar wave equation. The procedure is totally generic. It has nothing to do with the wave equation. Basically, what one does is one introduces new variables to absorb intermediate derivatives. For instance, in order to get rid of this second spatial derivatives, one puts in new variables for the first derivatives. So we define a new set of variables, phi I, as c times the gradient of u. And no big surprise, this already now tells us that c times the gradient of phi, now we have two derivatives, is precisely the second derivative term we have over there in the scalar wave equation. And we also introduce a new variable, which we call pi, which is the time derivative of u. Whether one puts a minus sign in here is totally conventional. It turns out if you put the minus sign here for the scalar wave equation, we will have to deal with many fewer minus signs later on. And if you now take this equation here, the pi definition, and take its spatial derivative, so c times gradient of pi, that is, because of the definition we've just put down here, c times the gradient of the time derivative of u. Partial derivatives commute, so this is dt of di of u. And di of u we had called phi earlier on. So this is minus c phi. But this is c di of u is just phi, so we have tt of phi I. I am missing a minus sign, thank you. Indeed I do. And so what we now have is that instead of writing our equation in second order form, we can write it as a set of first order equations. Let me collect all the time derivatives on the left hand side. We have a time derivative of u and that is equal to minus pi. We also need time derivatives of pi and time derivatives of the phi variables. So let's see where we've got those. The time derivative of pi is the second derivative of u. So that will be our evolution equation. dt pi is minus dt squared u, so we need a plus c squared gradient of u squared. That's exactly this term over here. And we have the source term, so we have a minus s on the right hand side. And the dt of phi, I was already working out here from this condition. So dt of phi is minus gradient of pi. So this is what we get. And as promised, because I put the minus sign up here in the definition of pi, it turns out I now have two plus signs floating around over here. And so now the general form of first order equations is as follows. We have a set of variables. I label the variables with a subscript alpha. So the variables now are just the u I had beforehand, a pi and phi. So for the scalar wave, we have 5 variables now. And we have an evolution equation for those variables. They depend on space and time, of course. And these variables now are combined with their first derivatives, where in each of the evolution equation, in principle, all possible first derivatives can appear. So one way of writing it is to just put in everything that is around. First of all, we need all variables. So we will end up with a big matrix here with indices alpha and beta. And so we can have all combinations of alphas and betas mixing around. And we can also have all spatial derivative directions floating around as well. And these matrices here can depend on space and time, and they also can depend on the solution at the current time. So this is a schematic way of writing with summation over beta and summation over k all the different combinations of derivatives of all the different variables that are allowed. And on the right-hand side, we can have source terms for each of these equations. For the scalar wave equations, we had a source term for only 2 of the 3 equations. That can be the case, but that need not be the case. And these source terms could depend on space and time, but they can also depend on the solution itself, as it does, for instance, for the scalar wave. When just solving for the scalar wave, writing it in this quite abstract way seems overblown. But when we get towards Einstein's equations tomorrow, when we not only have a little wave equation, but many more variables, this is essentially one of the ways of keeping track of where things stand. And the other really important thing about writing things in first order form is that for this particular form, there is the biggest set of mathematical results about well-posedness, boundary conditions, and similar available. And mathematical results are important because if you look very carefully on what type of equations I've written down so far, there's actually preciously few. The first one I was writing down was an elliptic equation where the matrix A has only positive eigenvalues. The other one I was writing down was what turned into the hyperbolic equations. Where the matrix has precisely one negative eigenvalue and the rest positive. And then I was writing down this funny thing with the first time derivative and second spatial derivatives. I guess you could view this as a funny thing where you also have a matrix, and that matrix has 1, 0 eigenvalue. But if you now compare what we've talked about, elliptic, hyperbolic, parabolic, and compare this to all imaginable combination of second derivatives, this is a vanishingly small set of choices. If I were to ask my kids to write down a second partial differential operator, chances are they would write down something that would not be one of these, because almost everything doesn't fall into one of these categories and cannot be solved in meaningful ways. Okay, let's do a little bit of general theory of hyperbolic equations. And let me describe to you how one gets a handle on boundary conditions and also well-posedness and why all of these things hang together. This has to do with characteristic modes. Characteristic modes. And so what we are doing here, these characteristic modes are determined by the local properties of the equation by the short wavelength limit. So if you want to consider local properties of solutions, they are probed by short wavelengths. So let's try and take the high frequency limit and try to find solutions to our complicated general hyperbolic equation. So we're going to write down solutions u of x comma t in the form of some constant times e to the I kx minus omega t. So these are plane waves. They travel in some direction n hat, and they have a wavelength and the wavelength is related to the wave number that shows up here in this k by a 2 pi over lambda. So k 2 pi over lambda is the wave number, and the vector k I'm writing on the left is k times n hat, the propagation direction of the wave. If I now go to short wavelengths, this means I want to take k to be very, very big. And large k also goes along with a large frequency. But usually the ratio of the two, omega over k, this is the phase velocity. That will remain finite. So we'll write this as u0 e to the I k x n hat minus vt. I guess I should be careful whether I'm writing v's with a 0 or not, and I want to write them without the 0. And also what I have forgotten so far is that we still have multiple fields floating around. So when I'm writing u here, this is actually still a collection of fields. So this alpha parameter that labels through all the different fields we're evolving is coming along for the ride.
And the fields all have the same phase velocity here?
So far, we are looking for one plane wave solution. And that one plane wave solution can be a combination of all the fields. That's why we have the alpha floating around here. And that one specific plane wave solution has one specific velocity. But that we will find that we have multiple plane wave solutions at the end of the day that can have a variety of different velocities. So what the velocity is, we don't know just yet. Okay, so now what we want to do is we want the limit of k goes to infinity. Oh, but actually, before we take the limit, let's substitute. If we substitute this into our generic wave equation down here, what we get for the time derivative is the u naught alpha is a constant, it will just hang around. Taking the derivative of the exponential gives us a minus I k v e to the I k x n hat minus vt. If I now take the spatial derivatives, this is getting into a big mess. So we end up with first our big set of matrices. Now we need d by dk, so we get the u0 beta just hangs around. This is a constant. And if you take the spatial gradient of this term here, of the exponential, this gives us a I k and the kth component of the propagation direction n. Followed by the I, k, x, x n hat minus t, no change here. And the right hand side is the right hand side. This one hasn't changed at all. Everybody fine so far? Kind of, okay. Now let's take the life. Okay, now we can. First of all, let's divide this whole thing by k. This k drops out, that k drops out. We have a 1 over k on the right hand side. And now let's take the high frequency limit. After division by k, we now find that the right hand side becomes 0, k becomes large. And we also have everywhere the same overall factor, e to the ik, the same oscillatory factor, which we can throw away or divide by. And so what we now end up having is an equation that looks like, I'll write it, that looks like minus IV U0 alpha plus A alpha beta K n hat K U0 beta. I think there's another I floating around which I haven't cancelled yet. Equals 0. I will call this thing here P alpha beta. That still depends on the direction n of propagation. And if I now go one step further, I can write this as P of n alpha beta U0 beta equals V times U0 alpha. So, if we want to have plane wave solutions as a high frequency limit of our equations, and if we want to have the plane waves to travel in a certain direction n, then the distribution of these waves onto the different components of our set of equations, this U0 beta, how big amplitude we have in each of our evolved variables, and the propagation speed, V, has to satisfy this equation down there. So we have a matrix, P. This matrix multiplies the vector of variables U, and that must be equal to the velocity times the vector U itself. This is an eigenvalue problem. So, and at this point, we now have a bunch of different possibilities of what can happen. And these possibilities are going to map towards well-posedness. So the one that's really nice is the following. If this matrix P that we have floating around here is symmetric, well, or symmetrizable, doesn't really matter. Then we have a complete set of eigenvectors. Let me spell out eigen at least the first time. And all real eigenvalues. So with a complete set of eigenvectors, we can take any solution we have and decompose it in plane waves. So any solution is a superposition of plane waves. And because the eigenvalues are real, that velocity here is real, and therefore our plane waves are actually oscillatory things that don't blow up. So this is a really nice case. So, and here we now have a complete decomposition in oscillatory traveling modes. If I can't read my own writing, it's too bad. Then I need to write again. So this is one thing that can happen. Another thing that can happen is that we have to work more. The important thing up here was the complete set of eigenvectors and the real eigenvalues. And in the second set, we simply require that as the definition. If P of n has a complete set of eigenvalues, eigenvectors, real eigenvalues, then still we are fine. Everything is as above. And the only difference between the second group and the first group is that one has to work harder. Up here, if you can by inspection see the matrix P is symmetric, you know you're done, because you might remember from your linear algebra course that symmetric matrices have complete set of eigenvectors and positive eigenvalues. And real eigenvalues. So up here you don't have to work. If this doesn't work, then you actually have to look at the eigenvalue decomposition, go through all the details, and if you have done all the work and you find a complete set of eigenvectors and eigenvalues, you're still fine. All is fine, it's just more work. The third category that can come up is if P of n has all real eigenvalues, but not a complete set. This turns out to be bad. And the first set is that anything else. Okay, so those things all have names. The top one is called symmetric hyperbolic. The middle one here is called strongly hyperbolic. The third one is called, I have no idea where this name comes from, weakly hyperbolic. And the fourth one doesn't really have a name. The first two, where we have the complete decomposition in oscillatory traveling modes, this is where well-posedness lives. And the ones down here is where you don't want to go to. This is where things are bad, not well posed. So, I haven't yet told you what well-posed means. From my rather practical point of view, it's one of the fundamental criteria you need in order to solve numerical equations. It means that A, there is a solution, it is unique, and if you make small changes to your initial conditions, you're going to get small changes to the solution. So let me put this down in words. And let's stick with the uniform color. There is a solution, it is unique. Both of these are actually very important conditions to have. Otherwise, why are you trying to solve an equation?
Yeah. So when you say that the ADM formulation is equipoise, you mean that it's unique?
I'll show you in a second. And the third thing, it breaks down for the third thing, that the solution depends continuously on the initial data. So let me give you a counterexample, or let me first write down what this actually means in math speak. That if you take the solution of the norm of the solution at time t, that this is bounded by the norm of the solution at time 0. And it is bounded by something that at the worst grows exponentially. That's already good, if the solutions blow up exponentially. Now, the typical example of a not well-posed set of equations is a set of two variables where you have u1 dot equals the spatial derivatives of u2 and u2 dot equals 0. So this is a matrix. This has now a characteristic matrix of 0, 1, 0, 0. Because this is a one-dimensional problem with only x, there is no n hat floating around and there is no extra k index floating around. The eigenvalues are both 0, and there is only one eigenvector, and that is 0, 1. So this equation lacks the second eigenvector. It doesn't have a complete set of eigenvectors. And now the bad thing that can happen here is this one. Take as initial guess. So we have u of x comma 0 plus 0, u1. And we have u2 of x comma 0, epsilon sine kx. So because of the epsilon, we can make this u2 arbitrarily small. So we have a norm of the initial data that will be an epsilon. I'm somewhat vague here what I mean by norm because it doesn't really matter too much, and because I would need to consider fall-off conditions to become precise. However, if you now take the time derivative of these things, what you find is that u1 of t, u1 dot, is equal to minus epsilon k cosine kx. u1 dot has the spatial derivative of u2 in it. u2 is the sine kx that brings the k in front. And so u1 of t will grow like epsilon k t. And so we will have that u at some time t will grow as epsilon k t. And so the difficulty is now that the solution blows up ever more quickly the larger k becomes. So if you have initially really high frequency perturbations in the initial data, they blow up arbitrarily quickly, the faster the smaller k is. If you now try to solve this on a computer, you start with initial data 0, say, but computers always have 10 to the minus 16 noise in the data. This 10 to the minus 16 noise will trigger this type of nesting mode, which will then grow linearly in time. If you now try to solve this with higher resolution, you have a finer grid. The grid can support shorter wavelength modes. That shorter wavelength mode will blow up more quickly than before. So as you increase the resolution in your computer simulation, the higher the resolution, the quicker it will crash. And my understanding is, coming back to the ADM equations, that somewhere in ADM this type of behavior is lurking as well. Okay. Now, on the verge of the break, let me point out that all this characteristic decomposition, the eigenvalue analysis, is not only important to figure out well-posedness, it also has another excessively nice application. If you consider boundaries of your computational domain, so here's the picture I drew earlier. Here's omega, and here's now going up a time-like boundary with some normal n hat. We've just said that given n hat, we have a decomposition into traveling modes. That travel along n. we have some of these modes that have, say, velocity positive. Those modes are happily traveling out of our computational domain. So for these modes that are traveling out of the computational domain, those we want to leave alone, and there one does not need to apply a boundary condition. And then there's modes that are traveling into the computational domain, v less than 0. Those are incoming. And here we do need a boundary condition. So the characteristic decomposition tells you how many boundary conditions you need at each point on the boundary. It depends on how many modes you have with negative v. And it also tells you how to impose boundary conditions, that you need to put a boundary condition on the relevant linear combination of all your fundamental fields that are forming the eigenvector of that particular mode. Okay, and I think this is a good point for a break. Are there any questions before the break still? I guess I've worded this the wrong way around.
I was a bit confused about like the symmetric what do you really mean when you say like a complete set of eigenvalues and then see that here this matrix is non-degenerate and of course we see one.
Yeah. Okay, thank you. Oh dear.